Hi everyone, I'm Ghazaleh. I'm a research assistant at SeNDA Research Group of UAB. I'm here to present a paper recently published named Federify with my co-authors Christina, Guillermo, Jordi, and Habib. And basically this is about a federated learning scheme, verifiable federated learning scheme with the help of zkSNARKs in blockchain. And here we'll start with the federated learning. What actually federated learning is? Well, it was first mentioned by Google's research, and basically what they said was like a collaborative method of training a machine learning model. And instead of having all the data at one center and sending all the data to a central server to train the model on, basically each person, each entity has their own data in their own device, train the model, and the model is this thing that is going to be sent somewhere instead of the data. But why? Well, basically, to ensure privacy. Let's go with an example here. It was first mentioned in Google Keyboard. What happens is that, let's assume that Google Keyboard was not trained this way. So what will happen is that for you to get suggestions on your keyboard, you have to send all your chats, all the things that you search in Google and whatsoever to a central server. So it will train its model based on your data and then give you suggestions, which basically is nothing that any one of us wants. It's like giving everything, all the data, all your inputs to your phone into a server that you don't know. So that's why that Google came up with federated learning, just to ensure privacy. But, well, there are still some concerns even though we are using something like this. So I told you that we're not sending the data to a server, but we're sending the model to a server. So what happens is that there could actually be privacy attacks based on the model that you send. Although you're sending me a trained model of the chats that you have done, I can, based on some inferencing methods, understand if a certain data is in your dataset or not. Or I can actually understand if there is a property in the dataset that you're using or you're having. Or in the worst case is that I can basically reconstruct all your dataset just based on the model that I see. Apart from all of this, in the traditional machine learning, I told you that the data are going to be sent to a server, and if I'm the person who wants to train the model, basically I am training it, so I'm sure that I'm training it correctly. I'm sure that I'm using the correct data. But what happens is that if other people are going to train the model, basically you don't know if the model is trained correctly, or you don't know if they're using the correct data. Or I told you that instead of having the models, instead of aggregating all the data points into a server, we're aggregating the models to a server. So let's assume that you're the people who want to send your models to me to aggregate, but how are you going to be sure that I am putting your models all together correctly? So although federated learning solves the problem that you're not going to send your data to a server, it comes up with all these new concerns, let's say. And well, let's dive a little bit deeper into the structure of a federated learning. So as I told you, let's say that in this room, we're going to train a model. What happens is that all of you use your own data on whatsoever device that you have and train a model like this. Okay, so you basically train a model, a really small model, basic with just your own data, and instead of using that model, you send that model to a server here. So this server uses all your models, creates a global model, which is basically with the help of all of your data, which makes it more general, which makes it with a better accuracy, and then that will be the model that we have in comparison to the traditional way of training a model. And so I told you that all of you are going to send your models to me, let's say, as someone who's going to gather all the models. What will happen is that, well, we can just send your model to a trusted server, let's say a server like on whatsoever, we don't mind. But the thing is that you have to trust them because they're going to do whatsoever and you don't know how they're going to combine all your models there. Or what will happen is that a better version of that is actually using a server or choosing a server that is like, it's been chosen. So you know, based on a reputation method or like voting or some other schemes of like game theoretic solutions, that server is more trustworthy. Or you can even do better and distribute the trust. So what will happen is that all of you can send your models to a blockchain, and that blockchain, the nodes of that blockchain can actually gather all your models all together. Well, what we do is that we take this blockchain, but we make it automatic. So basically, instead of having nodes, all the models are going to be sent to a smart contract automatically combined together. So I told you that one of the problems, one of the concerns was the fact that how are these models going to be put together? Well, basically, this is the solution. We're okay with putting all the models together, but the local models. So I also told you that if you're not the one who's going to train your model, you basically don't know if the person who is training the model is doing a good job. So what happens is that they're going to do some local training based on their own data, and they're just going to give you some numbers, and they're going to say that, okay, this was the model that I trained. But are all the local models correct? Well, we can kind of understand if they're correct or not. Based on what? Well, basically, they're cross-validations, that each model is tested upon a test data set of another person, another entity in the scheme. Or you can just have a global test data set. Let's say that all of you here train your models, and instead of like you receive another model and you want to see if that model is correct or not. We have a global test data set here, and you will just put that data set, run whatever measure and method of getting the accuracy of the model on that, and see if the model is correct or not. And this is more or less the same, just basically using different methods and metrics. Or what will happen is that, let's say that all of you, based on how good you train the model or whatsoever, you get a reputation score. So the ones that are doing a better job are the ones who are going to be given more value of their models. So they're going to be, their models are more acceptable. We know that they're doing like they're not doing anything malicious. And what are our solutions? Instead of all of this stuff, you can basically do one thing, is that you train your models, and you, after training this, instead of just giving me your model, instead of just giving me some random parameters, some random variables, you give me a proof as well. This is what zkSNARKs are. You give me a proof that all the computations that you did, all the model trainings that you did were done correctly. So our solution here is actually zkSNARKs. So what do we have up until here? Is we have some data owners, as I said, like the devices that you own and the data, the private data that you have in them. And these data owners would send their models to the blockchain, and the blockchain can actually make sure if the models were trained correctly. So you're not giving your data to anyone. You're not, if you do anything malicious, if any one of these data owners doesn't train the model correctly, the blockchain can understand this by the zkSNARKs, so by the proof that they provide. But is this enough? Well, basically, do you remember I told you that you're not sending your data to a central server, but you're sending your models to a central server. If we do what we did before, if we do this, you're still sending your models to a blockchain. Blockchain is completely public, so everyone's going to be able to see your models. What will happen is that they can still inference data, information from your model, which is not something that we want. We don't want anyone to inference any information from our local data. So the solution. There are two solutions, more or less, is like either you add some noise, basically you hide your models. Let's say you just add random stuff to your model, which would not necessarily change the model's accuracy or so, but I, as a third party, will not be able to understand your models completely, which, as it mentioned here, it's a differential privacy, so it does not deliver complete privacy to your models. Or we can do what? We can just encrypt the models, which is basically complete privacy. You just encrypt your model, you send it to another, wherever that you send it. No one will be able to understand anything from your model, infer any information from your model, except you just give them the key. But it's still not enough. And our solution here is like a homomorphic multi-party computation. Why? So let's assume that we're in the previous structure, which is basically now we're here at Federated, the complete version of Federated. What will happen is that I told you all data owners have their data privately, train their local models, encrypt their local models, give it to blockchain. The blockchain would check if the model was trained correctly, and if it was trained correctly, it would accept the model. So basically, everything up until now is completely okay. You have encrypted models, you have verification of the everything and whatsoever. But one thing, we said that the models are encrypted and sent to the blockchain. Let's say that the blockchain needs to add all of your models together. What will happen here? What you're sending there is basically an encrypted version of your model. Either the blockchain, the only reason here is, the only solution here is that for the blockchain to decrypt your models, add them together and encrypt it. But the blockchain is public, so if you decrypt your models here, basically everyone's going to see it. That's why that we used homomorphic encryption. With the methods that we use, when you send your model encrypted to the blockchain without even decrypting it, the blockchain is going to be able to add all of your models together and still in a decrypted version. So no one's going to understand anything from your model. And well, where does these people come from? It's basically like, let's say, in each decryption, we have a public key and a private key. If we say that just one person is going to have the private key for all these like encrypted models, what would happen is that that person at any moment can just decrypt the local models or the public global model and whatsoever. Like you're trusting that one entity with all the information in all your schemes. That's where these people come from. That's why this is a multi-party homomorphic. Basically, the encryption key is distributed between all these people, so no one in this scheme is able to decrypt the model by themselves. That's how we get to full privacy, more or less almost solving all the problems that we mentioned before in federated learning. And diving a little bit deeper into how this was done, basically, these are data owners. So the data owners do train their models based on the private data that they have. They create a proof. They send the proof with the model to a blockchain. This is a smart contract on the blockchain. When they send the model and the proof to the blockchain can actually make sure if this proof, if this model was computed correctly. If the model was computed correctly, it would just take the model as a corrected model. Well, basically, it's done. On this part, it's done. One of the entities just trains their model, send it to the smart contract verifies it, and it's complete. Let's say that in a whole training set that we're doing, multiple entities, let's assume that DO1, DO2, DO3, DO4, up until DON, send their models, the smart contract completely verifies them, and we have the global model. But the global model is encrypted. What will happen is that where all these other people come into the account, into the scheme, they do the decryption one by one because it's a multi-party decryption. None of these people can do it, if you remember, none of these people can do it by themselves. So they have to all come together to decrypt the global model. What will happen is that they decrypt the model, each one for themselves. They send the decrypted model, partially decrypted model with the proof as well to the smart contract. The smart contract, if verifies the proof, it accepts the partially decrypted model as well. So basically, all the computations done here off the blockchain are verified, and more or less everything is decrypted, except for the global model when you decrypt it. So, I mean, almost all the problems are solved. But let's go through a recap of what we did. It's like we resolved the privacy issues regarding the model and data with encryption. So when you encrypt your model, no one's going to see anything from the model, and no one's going to be able to infer anything just by your own model. They see the global model, which is an aggregation of all the models, but not your own model. We mitigate model poisoning. We completely resolve the problem of model poisoning by the help of verification, by the help of zkSNARKs. We conduct automatic and fair aggregation with the help of smart contracts. So basically, the aggregation of all the local models are done on the blockchain, and it's public, and it's automatic. So no fault is going to be happening there. Also, we did a full implementation of the scheme, which is available on the GitHub and with this QR code here. But, I mean, I've been up until here saying that we've solved everything, but definitely it's not correct. What happens is that the model that we implemented with this scheme actually was a really, really simple model. It was a naive Bayes classifier, which is more or less the simplest classifier that you can choose. And where to solve is like actually using a more practical classifier. But why we cannot actually, we were not able to do this is that the zkSNARKs and well, ZKs more or less are very like resourceful, and the proving schemes are more or less, let's say, resourceful well. So it's like computation overhead is a bit high. And what we're looking into at this moment is using maybe different ways of, different methods of ZKs, or different ZKs, or actually come up with a better or a more efficient or optimized verification scheme. On the other hand, what I told you is that, yes, we verify if the models are trained correctly, but the thing is that we never know if the entities training the models actually use the correct data or not, which is another, well, currently the research that I'm working on at this very moment. And that was this. Thank you for your time.